So for this final exam review, we're going to be reviewing the properties of exponents and also exponential growth and decay as an application. So very first property we need to remember about exponents is how to deal with multiplying two terms that have the same base. So in this case we have a squared, number one has a squared times a to the fifth. So the easiest way would be to tell you that the answer is a to the seventh. To tell you when you multiply, you add the exponents. The problem is when you multiply, that phrase isn't really that specific and we tend to misapply the rule. So the idea here is a squared is really a times a, and a to the fifth is really a times itself 5 times. So when you think about this, we would say we have 2 a's times 5 more a's would give us 7 total a's, or a to the 7th. So instead of writing out this every time, we talk about the rule, which is a to a power times a to another power. You would just simply add those powers together. And that's true for problems like 1 and 2, and even eventually 5. But if you look at number 3, that's a slightly different structure. What we have a tendency to do is add the two numbers together, 2 and 8, and say b to the 10th, but that's not correct, and we'll talk about why here in a second. So again, a squared times a to the fifth is a to the 7th. If you're ever unsure, you can always write it out, or at least start writing it out and get an idea or a feel for how that works. Number 2 is pretty similar. The only difference is the first thing I would do is consider that x to the 0 is 1. Anything to the 0 power is 1. So that's the first thing I'm going to do. And then the rest is really 1 times x cubed is just x cubed. There's really nothing else to do beyond that. Now, like I already mentioned, number 3 is not the same as b squared times b to the 8th. This is what we call a power raised to a power. So it's b squared raised to the 8th power. And the shortcut would be to tell you that the answer is b to the 16th. You multiply the exponents, and that's true, but here's why you do that. B squared to the 8th really means b squared times itself 8 times, which I wrote out here. So then you could say, oh, well, I have 2, 4, 6, 8, 10, 12, 14, 16 b's, and say b to the 16th. Because if you write it out like that, it really becomes a problem much like number 1, which is a base raised to a power times the same base raised to a power. You add all the exponents. Now the shortcut would obviously be to say, I would like a rule so I don't have to write it all out. When you have a power raised to a power, the exponents would be multiplied. So this case would be b to the 16th. Now how is number 4 different? Well, now we're dividing exponent terms. So what I do is really try and mentally or even physically separate the coefficient from the variable term. They're multiplied, but it's only q that's being raised to the 8th power, not 4. And then what I do here is really just reduce. That's how I want to handle this. So I have a 4 in the top and an 8 in the bottom. So those reduce. I could divide them both by 4. So they can reduce to 1 over 2. And then the way I think about it is 6 q's in the bottom and 8 q's in the top. The 6 in the bottom will reduce with 6 in the top, leaving just 2 in the numerator. So then my answer would be q squared over 2, and that would be it. Now if you're unsure as to why that works out, if you wanted to, you could write q times itself 8 times and q times itself 6 times in the top and bottom. And then for every 1 in the top, you reduce with 1 in the bottom, and you'd be left with 2 in the top, which is why that's q squared. Number 5, before we can multiply the two parts together, we first have to deal with that exponent. So mn, all raised to the 2nd power, really means you take each part inside that quantity and raise it to the 2nd power. Using the word distribute isn't really correct because you're not distributing the squared, you're just squaring each part. I know that's a really like a very fine line, but mathematically speaking, it's not called distributing. You're really just raising everything inside to this 2nd power. So first thing I would do that. M squared, n squared times m cubed, and then I can just handle the m's together. So m squared times m to the 3rd, they're the same base. You'd add the exponents, m to the 5th, and then n squared stays n squared. So that's how you handle something like that. Number 6, you'd handle similarly. Watch how I write this. The first thing I would do is write each thing inside that first quantity raised to the second power. You may or may not have to write this step, but I definitely like to, just because it helps me keep straight what I should be doing. And then we'll leave that second quantity alone. So now I have negative 3 raised to the second power, which is 9, and x squared raised to the second power is x to the fourth. And then I'm going to multiply that by that second quantity, so then I would multiply the numerical parts. 9 times negative 5 is negative 45, and then x to the fourth times x to the fifth is x to the ninth, and one of them has a y term, one of them doesn't, so it's just y to the fourth. So I had to deal with that exponent first, and then multiply the two parts together. Number 7, similar. I'm going to handle that quantity raised to the third power first. So I'm going to take everything in that first set of parentheses and raise it to the third power. And then that'll eventually be multiplied by 4xy squared. So then 3 cubed is 27. X squared cubed is x to the sixth. Be careful, we have a tendency to just go fast and call it 5. We're not adding those. It's 2 raised to the third power. Should be 2 times 3, which is x to the sixth. And then that, by the same reason, that should be y to the 12th, and then we'll leave that second quantity alone. I no longer need in parentheses because it's just being multiplied by that first quantity that's been simplified. And then I would multiply the numerical parts. 27 times 4 is 108. X to the 6th times x to the first is x to the 7th. You add the exponents, and y to the 12th times y to the second. You'd add them, you get y to the 14th. So that should be your final answer. Number 8 is a division of two variable and numerical parts. So what I do is like to think about, I'm going to write it, but this is really what I'm thinking about. 20 times x to the 6th times y to the 7th, 4 times x to the 3rd times y to the 5th, and then I'm going to reduce the corresponding parts. So reduce the numerical part, reduce the x's, reduce the y's. So 20 and 4 reduce to 5 and 1. 3 x's in the bottom would reduce with 3 x's in the top, leaving 3 in the numerator and none in the bottom. 5 y's in the bottom reduce with 5 y's in the top, leaving 2 y's in the top and none in the bottom. And then just multiply what's left in the top and the bottom. Everything perfectly reduced in the bottom. So all I'm left with is 5 times x cubed times y squared, and that's how that would simplify. Number 9, I have 5x to the fourth times 3x squared. What I like to do is think about multiplying the numerical parts. So sometimes I rearrange them, sometimes I don't. Really in my head is how I would do that. I'd notice it's 5 times 3, so I'm going to end up multiplying those, and x to the fourth times x squared, I'm going to multiply those. So I get 15, and x to the fourth times x to the second is x to the sixth. You don't have to write the rearranging of that. It just might be a helpful thing to do to get all your numbers next to each other and all your like variables next to each other. So 10, I really have 24 times x squared times y to the 8th, and I'm going to separate the bottom similarly. And then I'd want to reduce the numbers and then reduce the x's and y terms and see what I have left, or x's and y parts, they're not technically terms. So 24 and 8 reduce to 1 and 3, they both divide by 8, and then 2 x's in the top would reduce with 2 in the bottom, leaving 4 in the bottom. 3 y's in the bottom would take away 3 y's in the top, leaving 5 in the top. So if I look at what's left in the numerator and what's left in the denominator, I just have 3y to the 5th in the top and just 1 x to the 4th or x to the 4th in the bottom, and that would be simplified. Number 11, 3a to the 5th all raised to the second power. What I like to do is write each part raised to the second power. So 3 to the second, and then a to the 5th to the second. So 3 squared is 9, and then a to the 5th squared, where you would multiply 5 and 2, and you'd get a to the 10th, and 9a to the 10th would be your final answer. 12, I have 3a raised to the second power times 4a cubed. So what I would do is raise each part of the first quantity to the second power. So 3 squared and a squared, and I'm going to end up multiplying that by 4a to the third. So 3 squared is 9, a squared is a squared, so I end up with 9a squared times 4a to the third, which is 36a to the 5th. Number 13, I have a little bit going on in the numerator, so the first thing I would do is notice I have 4 raised to the 0 power, and that's going to be 1. And then I have x squared raised to the 4th, which would be x to the 8th. You would multiply those exponents all over x to the 5th, And then I would reduce 5x's in the bottom from 5x's in the top, leaving 3x's in the top. So I'm left with just x cubed as my final answer. And then number 14, there's a couple different ways to handle it. What you'll notice is I have a fraction with variables and numbers in each part, all raised to the second power. So you can either take everything on the inside and square it and then reduce, or what I like to do is actually reduce the inside as much as possible and then square the result. So what I mean is, notice I have 18 and 20, so those are both divisible by something, right? They're both divisible by 2. So I'm going to write it out all separated so it's a little cleaner to see how it reduces. So if I divide the top and bottom numbers by 2, I would see I'd get 9 and 10. And then 1x in the bottom would reduce with 1x in the top, leaving just 3x's in the top. And then 6x's in the bottom reduced with 6x's in the top, leaving 3y's in the top. So what I have now is 9x cubed y cubed all over 10. That's still all being squared. I haven't dealt with that squared yet. So now I need to square each part on the inside. So 9 squared is 81. X cubed squared, you'd multiply the exponents, you get x to the 6th, y to the 6th over 100, and that would be your final answer. I think this approach is a little bit better than trying to square 18, square 20, and then reduce. You're dealing with smaller numbers when you reduce first. So that's how I approach any problem like that that's a fraction raised to a power. Then 15, what I like to do is think of the coefficients of my variables and then my variable parts and multiply. So I have 3 times x to the 4th times 4 times x squared times, and then the coefficient of the last one is really 1. So I multiply the numerical parts. 3 times 4 times 1 is 12. And x to the 4th times x to the 2nd times x to the 3rd, you would add all of those exponents and you would get 9. And then that would be it for that one. So those are some basic exponent rules. There's a few more problems we'll deal with in a little bit, but we've covered multiplying, dividing, and then power raised to a power. So the next few problems are what we would call exponential growth or decay problems. Essentially what's happening is something is growing or decreasing by an exponential amount, meaning it's not following a linear path, but following what we would call an exponential curve. So it's either starting off really slow and growing really fast, or starting out really high and really decreasing and then slowing over time. So it's not a linear model for growth or decay, it's an exponential, and there's a function associated with that. And the function is this: y equals c times the quantity 1 plus or minus r over t. Now, that plus or minus, it's not both, it's one or the other. And we'll talk about when it's one or the other. But that's kind of the structure of the equation. So I want to point out what each part stands for before we get into a specific problem. So if y equals, that's very common, we're talking about a function. Now c, that number out there is always your initial amount. So whatever we're dealing with, that whatever our initial amount is in the situation will always go out front of our quantity. And then 1 plus or minus is part of the function. The only other variables we'll need to plug in for are r or t. And r stands for your growth or decay rate. So something's growing or decaying by a certain percentage rather than a certain amount. When things grow or decay by an amount, that means they're growing linearly. When they grow or decay by a percentage, they end up growing what we call exponentially. So that is going to be your growth or decay rate. Your rate is usually given to you in a percentage. In the function, we need to write it as a decimal though. And then t will stand for your time interval. That could be minutes, hours, days, years, months, depending on what the situation is. So that's kind of the structure of the equation. Once we read through the problems, we'll be able to kind of identify the parts and put them in place. And these definitely rely on our ability to use our calculator for these. But let's set one up. So 16, a principal is another way of saying an initial amount. So a principal of $800 is deposited into an account. So putting $800 into account, when we talk about paying interest, what that really means is the longer we leave that money in an account, the more interest that's added to that amount. So interest could either be a good thing or a bad thing depending on the context. When we're talking about investments, interest is great. When We're talking about loans, however, interest is what we end up paying back in return. So it's still works the same way, but one is a positive context, one's negative. So in this case, we're getting paid interest for our investment, our deposit. So we're earning 5.4% interest, and we're going to leave that money in the account for 6 years. So what should happen is, over the course of 6 years, our $800 should grow by 5.4% each year, which isn't going to be the same amount every year because it's always a percentage of the previous year. Not that we need to go in that in depth, but that's what makes it form a curve. The more money you have in there, the faster the money grows. So in this case, what I like to do is identify the pieces. So 800 is going to be our principal. And so I'm going to call it C. C is 800. 5.4% is our rate, but we want to put 5.4% as a decimal. So the way you do that is you take 5.4 as a percentage and you move the decimal place 2 times to the left, which is 0.054 as the decimal. And then the time that this is going to be in the account is 6 years. So I have my 3 variable values. So here's what I like to do. I like to write the equation. C times 1 plus r to the t. The reason why it's a plus here is we're talking about exponential growth. This money is growing over time. So then if I replace all of my variables with the numbers that I said they are, notice it's 1 plus whatever my rate is, raised to the 6th power. You would literally type in your calculator 800 in parentheses 1 plus 0.054 to the 6th power. So you'd raise that quantity to the 6th, and what you should get is 1096.815.685. That's the whole decimal that appears in my calculator. So what I want to talk about now briefly is how to round. If we're talking about money, it makes sense to round to cents, 2 decimals. So I have 2 acceptable answers here. So if I want to round to 2 decimals, imagine putting a line after the second decimal. And here are the regular rounding rules. If the number after that line is bigger than 5 or bigger, you round up. If it's less than 5, you round down. For me, I would take either a rounded value or you just put a line there and chop off the rest. I would take either. So what I'm saying is the 2 answers that I'll take are 1096.81 or 1096.82. I would take either of those, but I won't take anything else. So be careful how you type it in. Make sure your decimal is in there correctly. All raised to the 6th power. I don't care if you round or if what it's called truncate, where you essentially just chop off the rest of the decimal after the second one. I'll take either one. On a multiple choice, though, you would have to make sure you match the correct one, because it could have like 82 and not have 81, so you'd have to be able to be flexible in that regard. So 17, though, we would handle very similarly, right? We're going to set up the equation by identifying the parts. So our initial amount is the deposit, which is $45,000. John deposits $45,000 in an account. The rate is 6%, which is 0.06 as a decimal. And we're going to leave the balance in there. Sorry, Joan is her name, not John. What is her balance after 10 years? T is going to be 10. So the setup would be very similar to the last one. I usually write the equation as is, without any variables plugged in. C, 1 plus r to the t. Again, it's plus in this case because we're talking about exponential growth. And then I'm just going to put the numbers in place of where they go. So 45,000, 1 plus 0.06 to the 10th. And you don't have to do anything on the inside. You just type that in your calculator and you should get $80,588.14634. And again, for the 2 answers I'd accept, you could either round it after the second one or truncate it. So my 2 acceptable answers would be in dollars, so put a unit on there, 80,588.14 or 80,588.15. So if you think about it, $45,000 almost doubled in 10 years without doing any work. So that's essentially how exponential growth works. 6% starts to grow really fast over time. So 18, talking about farms in the U.S. So make sure you read through the problem and identify each part. It says the number of farms in the U.S. decreased by 2.1% each year. So 2.1% between 1960 and 1990. It said in 1960 there were 4 million farms. So starting in 1960 there were 4 million farms. Then that number of farms goes down by 2% each year. So if you think about setting this up, C is going to be 4 million. And then because we're talking about the number decreasing, R is going to be 2.1% as a decimal, which is 0.021. And they're asking for an equation, which means we're not actually given a time to plug in. We're just asked to write an equation where t is essentially going to be our other variable. What I mean by that is I should get y equals 4 million on the outside, and then on the inside should be 1 minus 0.021. Has to be a minus there because the number of farms is decreasing every year. And then it should all be raised to just t, because we weren't told how long. People have a tendency to want to put 30 in there for a problem like this. It's not asking how many there were in 1990, just asking you to write the equation. That would be the equation. You don't even have to combine the terms in the inside. You just leave it like that, and I would take that. So that would be our equation. But again, if I did 1 minus 0.021, I would get the decimal 0.979, which is possible that you might need to recognize that in there, but that's fine for me for the equation, and that's your answer. Number 19, similar to number 17, talking about depositing money into an account that pays interest. So initial deposit is $25,000. The interest rate is 5.6, which as a decimal is 0.056. The difference here is it says how much is in the account in 2006. Well, that doesn't mean it was in the account for 2006 years. In problems like this, you'd have to compare it to what year the deposit was made. So if we're talking about the deposit being made in 1990, from 1990 to 2006, that's 16 years, which means t is going to end up being 16 in my equation. So my equation is going to be y equals 25,000, and then it's going to be 1 plus 0.056, plus because we're talking about exponential growth, to the 16th, because 16 years from 1990 to 2006, and then I would literally put 25,000 times 1 plus the quantity 1 plus 0.056 to the 16th in my calculator, and you should get $59,780.93452. In this case, the number after the 3 is not 5 or greater, so you're probably only going to come up with the answer $59,780.93. And then some more simplifying. The difference with these ones is we'll talk a little bit about a negative exponent will appear. You'll see that in a couple of the problems, so we'll refresh your memory on how to handle that. Number 1, though, 7x to the 8th times negative 3x to the 3rd. As you get more comfortable, right, you just multiply the coefficients. 7 and negative 3 is negative 21. X to the 8th times x to the 3rd. You add the exponents to get x to the 11th. Number 2, I like to split the coefficient from the variable part just so I can reduce a little bit cleaner. So 32 over 16 can reduce to 2 over 1. And then the 2 x's in the bottom will reduce with 2 x's in the top, leaving 6 x's in the top, or x to the 6th. So I'm left with this 2x to the 6th in the numerator, and then 1 in the denominator, which I'm not going to write, just 2x to the 6th. Number 3, I have negative 4x to the 3rd, all raised to the 2nd power. So what I like to do is write each part to the 2nd. I know we maybe don't want to write that, or we want to try and do that in our head. That's fine if you can handle it perfectly, but we have a tendency to not deal with the negative correctly and then also call it like x to the 5th. So what should happen is negative 4 squared is positive 16. X cubed squared, you would multiply the exponents to get x to the 6th. So if you don't want to write that middle step, you're really just squaring each thing on the inside, and as long as you can do that correctly, you should be fine. Number 4, 5x to the 7th, y to the 4th, times 4x cubed y. Really, you're going to multiply the number parts and the common variable parts. So 5 times 4 is 20. X to the 7th times x to the 3rd is x to the 10th. Y to the 4th times y would be y to the 5th. You don't have to, write them all out or show a bunch of work, as long as you remember when you multiply x to something times x to something, you would add the exponents, and the same for y. Number 5, a slightly different problem. What you'll notice is it's still a fraction, but if you look carefully in the bottom, there's this negative x to the negative 4th down there. So if you remember how we handled that, anything raised to the negative power is really just notation for the reciprocal. So when we have a fraction already, essentially what that x to the negative 4th does is move up So since it's in the bottom, it moves to the top and becomes x to the positive fourth. So what I do is kind of split everything in the top up, 12 times x to the fifth times y to the eighth, and that x to the negative fourth that was in the bottom is now x to the fourth in the top. And then what's left in the bottom is 14y to the sixth. And now I'm going to reduce this like I reduced previous problems. So 12 and 14 will reduce to 6 and 7. I have 6 y's in the bottom and 8 y's in the top. So 6 in the bottom will reduce with 6 in the top, leaving 2. So y squared. And then now that my x's are both in the top, x to the fifth times x to the fourth is x to the ninth. So what I should get is 6 x to the ninth y squared all over 7, and that would be your final answer. So the first thing I like to do is deal with the negative exponents and then worry about reducing. Number 6, the answer unfortunately is not 1. We have a tendency to just see something to the 0 as 1, but remember, what I've been doing the whole time to alleviate that is I really think of this as 7 times x to the 0. Now that I've really split those, multiplied them, it's really clear that only the x is being raised to the 0, which means it's 7 times 1, which is 7. And that would be your answer there. Number 7, I have 8 to the third times 8 to the 7th times 8. And although it's not written, that's really 8 to the first. So if I multiply those, remember, multiplying, the base doesn't change, you just add the exponents. So it should be 8 to the 11th. For some reason, we have a tendency to, because they're numbers, want to call that like 8 times 8 times 8 and change the base. The base doesn't change, we just add all the exponents together. So you should get 8 to the 11th. Now 8 to the 11th is a super, super big number, so I'm fine leaving it 8 to the 11th, but if you put it in your calculator, it's something in scientific notation, so I don't really want you to write it all out. It's more complicated than just appropriately dealing with the exponents. Number 8, first, now that I'm dealing with the fraction, we've talked about negative exponents. I first want to peek and see if there are any. There aren't. The next thing I like to do is kind of split out each part, write them all as a string of multiplication, because it makes the reducing, I think, a little bit easier. So the 9 and the 36 reduce to 4 and negative 1. 2 x's in the bottom reduce with 2 in the top, leaving 3 x's in the top. 3 and y's in the top reduce with 3 y's in the bottom, leaving 4 y's in the bottom. So if I think about what I have left in the top, it's 4 times x cubed. And in the bottom, I have negative 1 times y to the fourth, which is negative y to the fourth. So that would be our answer there. 4x cubed over negative y to the fourth. Number 9, we have negative 3x to the fifth y, all raised to the third. So I like to split that out into each part raised to the third power. And then handle each part. Negative 3 to the third is negative 3 times negative 3 times negative 3, which is negative 27. X to the fifth to the third, you would multiply the exponents, get x to the 15th, and then y to the third is y to the third. And that would be your final answer. Number 10, I'm first going to raise everything in that first quantity to the second power. I write it all separately just so I can handle it appropriately. And then they'll be multiplied by 2xy to the fifth. So I'm going to square 4 is 16. So you get 16x to the 12th, y to the 6th, multiplied by 2xy to the 5th. And now I'd multiply the numbers. 16 times 2 is 32. Multiply the x's and add the exponents. Multiply the y's and add the exponents. And you should get 32x to the 13th, y to the 11th. Number 11, hopefully you notice that in the denominator there's a negative x to the negative fourth. So when I try and break this up, 12 times x cubed times y to the 7th, I'm going to multiply that also by x to the fourth because I'm going to move that x to the negative fourth up to the top, leaving me with just 6y to the fourth in the bottom. And then I'm going to reduce. 6 and 12 reduce to 2 and 1. 4 y's in the bottom, reduce with 4 in the top, leaving just 3 y's. And then the 2 x's, x to the third times x to the fourth would be x to the 7th. So I'd get 2x to the 7th, y to the third, all over 1. But I'm not going to write over 1. Just write that. Then number 12, here's where this one differs slightly from number 6. Notice 8x to the fifth is all being raised to the 0 power. So that means whatever's on the inside raised to the 0 power is just 1. That's slightly different than 6 because 6 was 7x to the 0, but only the x was being raised to the 0. if in number 6, 7x was all in a set of parentheses, then the answer would be 1, much like it is for number 12. So that's kind of the difference there on how to handle zero exponents. Number 13, we have a fraction raised to the second power. Again, the way I like to handle these is I like to reduce everything on the inside first and then square everything. So what I like to do is think about reducing that. So I'm going to write it all out, kind of separated by multiplication. You don't have to do this step in between, but it does make the reducing a little bit easier to see, I think. So 10 and 5 reduced to 2 and 1. 4x's in the bottom reduced with 4x's in the top, leaving 8x's in the top. And then 3y's in the bottom reduced with reduced with 2 in the top, leaving, or excuse me, 3y's in the bottom reduced with 3y's in the top, leaving 2y's in the top. So really what this becomes is 2x to the 8th y squared, all raised to the second power, which would be squaring everything on the inside. So 2 squared is 4, x to the 8th squared, you would multiply the exponents, and y squared would be y to the 4th. We have a tendency to call that like 4x to the 10th y to the 4th, but remember, you multiply the exponents when you raise a power to a power. 14, none of those quantities are raised to any exponent, so I can really just multiply the numerical parts and then multiply the x parts together. So this is going to be 5 times negative 3 times 2, which is negative 30, and x squared times x to the 4th times x to the 1st. You would add all those exponents together, and you get x to the 7th, and that would be it. Number 15, I have a fraction again. First thing I like to do is think of it as 3 distinct things multiplied together so that I could reduce the appropriate parts. 8 and 12 are both divisible by 4, so that becomes 2 and 3. 9x's in the bottom reduced with 9x's in the top, leaving 2, and 1y in the bottom reduced with 1y in the top, leaving 4y's. So what I have is 2x squared y to the 4th all over 3, and nothing else reduces, and that would be your final answer. Number 16, hopefully what you did before you just started multiplying is recognize that there's an x to the 0 in there. So I like to think of these all as separate things all multiplied together, because then this really becomes negative 3 times negative 4, which is positive 12, and then I have x to the 0, which is 1, multiplied by x to the 5th, which is just x to the 5th, and then y to the 4th times y to the 2nd. You would add the exponents, you'd get y to the 6th. 17, I have 3x to the 4th quantity squared multiplied by 5x squared. So first thing I have to do is deal with that squared on that first quantity. So I'm going to square each part of that first quantity. And then I'm going to end up multiplying it by 5x squared. So 3 squared is 9. X to the 4th squared is x to the 8th. And I'm going to end up multiplying that by 5x squared. So now I would multiply 9 and 5 is 45. And then you would add the exponents on your x. So x to the 8th times x to the 2nd is x to the 10th. And then the last problem here, still a fraction. First thing again I like to do is break each part of the fraction up into all multiplication and then reduce. So 7 and 14 reduce to 1 and 2. 5x's in the bottom and 5x's in the top actually reduce completely. And then 2y's in the top reduce to 2 in the bottom, leaving 7. So all I have left in the top is 1, and what I have left in the bottom is 2y to the 7th, and that would be your final answer. So hopefully after we've gone through these problems, you get a little bit of a feel for how I like to approach these problems. The work I write is not the only work you need to show or all the work you need to show. I might write some steps that you don't need, or you might be comfortable kind of going straight to a certain part, which is fine. I'm just trying to give as many tools as I can on ways that these exponents really work, because it is easy to mix these up. So hopefully these strategies are helpful. If you can remember when to add the exponents, when to multiply, and then when to how to handle negative exponents and zero exponents, you should be in pretty good shape for this topic.